All right, so let's talk about another example in which these Lewis structures might lie to you. And that's when talking about, are these electrons localized or delocalized? So localized just means that it only belongs to one atom. And so it doesn't participate in resonance. Something like this compound, for example. There's no resonance structures that involve this lone pair right here, and so they strictly belong to this oxygen, and so we say that it's localized. The other option is to be delocalized, and here you belong to more than one atom. Right? You're in some kind of conjugated system. You participate in resonance. An example of this would be a similar compound as the one to the right, except now we've got this carbocation over here. And so we can move this lone pair down here. And then we actually get a nice filled octet. So it will actually be the major contributor, right? And so let me draw this in purple, color code it. Right, so we can see that one of these lone pairs is actually delocalized. It belongs to both the oxygen and the carbon. And so here's where these Lewis structures are going to lie to you a little bit, or one example of this at least. Right, we have this compound right here. This is what's known as an amide. And so you're looking at this central nitrogen. And if I asked you what's the hybridization here, you'd say, oh, it's got 4 things attached to it. So it's sp3 hybridized, right? It's sp3 hybridized. But let's think about the resonance structures that it could involve in, right? We could move this lone pair over here, right? This is a lone pair next to a double bond. Kick the pi electrons up here. And then we'd end up with this structure. And in this case, now this nitrogen is actually sp2 hybridized. Right? Because it's only got 3 things attached to it. And it's true that the one on the left is the major contributor. However, we look at this experimentally and we see that this nitrogen is actually flat. It's trigonal planar. And so it is indeed sp2 hybridized, right? And so the things to remember here is that resonance structures stabilize the compound. So the compound will be the shape in which it is, or the hybridization in which it is, to have the most stability. And having more resonance structures results in a more stable compound. And so the other kind of like often quote that said is that shape determines hybridization. And so experimentally, we see that this nitrogen is trigonal planar, so it is indeed sp2 hybridized. So that's something that you have to keep track of. And this is, a fair question. If I asked you, what's the hybridization on that nitrogen? sp2 is the right answer. sp3 is the wrong answer. And if you think about it, it makes sense. What we have here is an oxygen, carbon, nitrogen situation. And then we have our sigma bonds, right? And then this carbon and oxygen are obviously sp2 hybridized. So we can have this pi bond right there from the unhybridized p orbital. And so if this nitrogen was sp3, right, it would look something like this, right? One of its sp3 bonds would be going like this. One would be going out. One would be coming out to the front of the board. And one would be going out to the back of the board, right, in order to get that tetrahedral shape. And so you see that these electrons cannot actually conjugate with this compound. They can't resonate. However, if we take a look at the other scenario, if the nitrogen is sp2, right, we have all of our sigma bonds, and then we have our unhybridized p orbitals. In this case, now this nitrogen has one, and now we can see we get this complete conjugation. We get this delocalization of these two electrons, right? So if your nitrogen is sp2, it can participate in resonance. And if it can participate in resonance, it's more stable, right? And so you're going to want to go towards the resonating structure. So the nitrogen here is indeed sp2. In both of these resonance structures, it is sp2 because none of these resonance structures really exist. And in the real structure, it's sp2 hybridized. However, we have to be really careful with this. And you really have to understand hybridization, what orbitals these compounds have, and what those orbitals are doing and what they have in them, right? So let's draw this compound here. This is known as pyridine. And so now you've got a lone pair next to a pi bond. And so you're thinking maybe I can push these over here, and then I could delocalize these electrons over here, and then I could have a resonance structure that looks something like this. And so we have to ask ourselves, is this okay? Is this okay to do? And so let's think about it a little bit in terms of hybridization and orbitals. Right? This nitrogen is obviously sp2 hybridized. And so that means that it has 3 sp2 orbitals and then 1 p orbital. Right? Remember that the p orbitals are what makes the pi bonds. Right? So the pi bond here is actually, its p orbital is in this, or it has these 2 electrons in it, right? That's what's making that second bond, right? So we've gone ahead and used up that p orbital. What we've got left now are 3 sp2 hybridized orbitals, right? You have one coming over here to form this sigma bond, another one coming over here to form this sigma bond, and then finally this lone pair is in an sp2 hybridized orbital. It's in an sp2 hybridized orbital. Hybridized orbitals cannot participate in resonance, and so you cannot do this, right? So this is not okay. So let me just write that out here. So the lone pair is in a hybridized orbital, and so it can't participate in resonance. And so the kind of little trick to kind of memorize this stuff, if this is what you want to use, my suggestion is just to do practice problems, and then you'll kind of get the flow of it. But the little kind of trick here is if it has a pi bond and a lone pair, the lone pair cannot participate in resonance. And that's because that lone pair is in a hybridized orbital because the p orbital is already filled up with electrons from the pi bond. And so this is kind of the same picture I drew up there, just kind of a little bit neater, not as cluttered. And so you can see that this nitrogen here is using up its p orbital to form this conjugation with the rest of the ring, leaving this lone pair as not in resonance, right? It cannot contribute to the resonance structures here. And then a similar scenario here with this oxygen, right? Think about what this oxygen is. This oxygen is actually also sp2 hybridized, right? And so its p orbital is in conjugation. So one of these guys is actually delocalized. while the other is in the sp2 orbital and is localized. Similar thing in this compound right here, right? These two electrons right here are localized, right? It's already used up its pi bond or its p orbital to make this pi bond. So again, just take a look at the work along sheet, get some practice in here, and be able to recognize that this is one of the trickier concepts.